Um, sorry, did you finish? Yeah, yeah, okay. Sorry, there's just been a bit going on in the room. Hi, everyone. We had a room booking failure today, so we're not in the room that we said we were going to be in. So sorry if anyone tried to find us in person and couldn't. So I'm just into my slides. Are they full screen? Yep. Okay. So let's jump into missing data. I'd like to see a show of hands or thumbs up if you have ever had data go missing in your meticulously designed studies, I'm sure. But when the data's come back, there's been missing data. There's some people. Great. And now the other thing that might have happened is that you got a data set with no missing data, but you think that maybe something happened before you got the data and all the NAs were deleted. Has that ever happened to anyone? That might be a statistician thing. Yeah, so missing data is a really, really common problem. And the take-home message from this seminar is that what really matters when it comes to missing data is why your data's gone missing. And there's lots of different reasons data can be missing, and that affects the way that you deal with it in your analysis. And that's why it's called 50 Shades of NA. It's really only 4 shades, yeah, it was a good title. So why do we worry about missing data? So there's 2 main reasons. It can lead to bias and it can lead to variance, higher variance. So you think about it, you're trying to estimate something, possibly a treatment effect. If your treatment effect estimate is biased, it means it's systematically lower over multiple repeats of your study. High variance is also a problem. That means each time you run your study, you'll get quite different estimates. So, sorry, this diagram source, it's a really classical diagram, this bullseye. So the red bullseye is the thing that you're trying to estimate, like your treatment effect. Each time you run your study, you might get an estimate that's a blue dot. And you can see that you don't want too much bias or too much variance in any study. And both of them are bad in that they lead to your estimates being far away from the bullseye. So where does our missing data come from? There's 4 main ways, and it can come in either your independent or your dependent variables. So structurally missing data, we're not going to talk about that much today, but that's just data that shouldn't exist. So for example, it could be age of your youngest child. That data won't exist for anyone that has no children. So it's sort of just is not meant to be there. And then we have data that's missing completely at random, which is where the propensity for any piece of data to go missing is purely due to chance and it's not related to your study at all. Data that's missing at random, and I'm going to go into all of these a bit more, so don't worry if you're just catching a bit of this. Missing at random is where missingness in one variable is related to some of the other variables, so the reason it's gone missing. And missing not at random is where the missingness, like the propensity for a value to be missing, is related to the actual value that's missing as well as other variables. And so these terms are coined in these 2 papers, Rubin 1976 and Marini 1980. And they're a little bit of a mouthful, a little bit confusing, but they are the main way that we talk about missing data in the literature. So missing completely at random, that's the first kind of non-structurally missing data. That's when data goes missing for reasons that are completely unrelated to study variables. So we can't predict which items might go missing. So a common reason that could happen could be a technical malfunction, like a power failure causes some samples to be lost, or a sensor runs out of batteries. It could be just bad handwriting, means that some values weren't transcribed into the final data set. Typos, you know it's wrong because it's got 5 more zeros than it's supposed to, but you don't know what it's supposed to be. And there's a lot of reasons why you can get missing completely at random data. So if you have data that's gone missing purely due to chance, you can delete the observations with missing data values, which is called listwise deletion or complete case analysis. And if you do this, you can still get unbiased estimates of your effects. So your effect, like for example, your treatment effect will be centered on the treatment effect that in the population. So why would we not always just delete the missing values when the data is missing completely at random? Just see if anything pops up in the chat. Give you a chance to say something. And I'll give you a hint. It's either bias or variance. Nothing's happening in the chat, so I'm going to keep going. Yeah, so it's variance. So it makes sense. We're reducing our sample size, so we're going to get lower precision on our estimates and then less statistical power than if we used all the data. So the more data that we throw away, the more power that we might be sacrificing. And you can see, depending on the pattern of missingness in your data. So here I've got a value missing in line 1, and I've got 2 more values missing down the bottom here, and I could end up throwing away quite a bit of my data if I just deleted all the rows with missing values. So it's generally agreed that if you only have a small amount of data that's missing and it's missing completely at random, a lot of different ways that you analyze the data is going to get you similar results anyway. So if you have a small amount of data missing and you are satisfied it's missing completely at random, then you can consider doing a complete case analysis, and that's technically much easier to implement typically. But if you have too much data missing and it's missing completely at random, you still shouldn't do a complete case analysis, even though you'll get unbiased estimates, because you should be worried about having less precision on your estimates. So everyone wants to know what's too much, what's not enough, what's too small, what's a small amount. There's, I found this threshold in a reputable source saying 5% is a small amount. So anything less than 5% is a small amount of missing data. If it's missing completely at random, just don't worry about it. But there isn't a universal threshold. There's 5 to 20% seems to be acceptable in the literature. But what it actually depends on is your sample size and your effect size. So if you have tiny standard errors already, then precision is not an issue for you. You're not worried about bias. So then you can do your complete case analysis and not worry about it. And you don't need to worry about statistical power. But if you are trying to reduce your standard errors, then that's when you might want to worry about it. So let's go through an example. This example is about a study that was conducted to evaluate the effectiveness of a new mathematics program for young children. So the aim was to evaluate whether the program results in greater skills gains as measured by NAPLAN than the existing teaching program. So we've got two programs. And then the secondary aim was whether the program is equally effective for students with differing levels of mathematical aptitude. So here's what the researchers did. They randomized the children into two groups to receive either the standard program or the new program. And at the beginning of the program, they measured the mathematical aptitude and the mathematical skills of the children at baseline. And they did this on 2 separate days because it was 2 tests. And then at the end of the program, they measured the mathematical skills of the children again, doing the NAPLAN. And let's say the children in this, they don't know that they're part of the study. It's a primary school, and it's a primary school that's got pretty good attendance rates. The tests were done in the middle of the week, and they were done in winter. So we got missing data in this study because sometimes children were absent on assessment days. So what assumptions can we justify here? Like, what reasons do we think that the children might have been absent? And I'm, just going to say it. The students were absent due to illness. So we're going to assume the students are absent due to illness because I'll just wait. We've got a little bit of sound interference here. Because these are young kids during winter. So the reasons that these kids are not at school is unrelated to either the treatment group, the treatment effect, or their baseline scores. It's just because they got sick. So because this is the assumption that we're making, then we're going to say the data is missing completely at random. So in this example, actually, because it was winter, 40% of students had one missing value across any variable. So there was 3 different variables: baseline skills, aptitude skills, or end of study skills tests. So what can we do? We think this is too much data to do a complete case analysis. We're going to try to account for our missing values. So in aim 1, we just want to evaluate the teaching program before and after. So what are our variables here? What's our dependent variable in this study? Is that going to pop up in the chat? See if someone can tell me the dependent variable. Yeah, it's the NAPLAN score. So this is our continuous variable measuring their mathematical skills, and we had some missing values in it. And then we also have some independent variables. We have time before or after treatment. So we measured the score before, we measured the score after. We have the treatment group, which the new program or the existing program. And these 2 variables have no missing values. And we also have the student ID, which also has no missing values. So we have missing values only in the dependent variable. So this is important because when the missing data is only in the dependent variable, we can use a linear mixed model, which is called maximum likelihood estimation, to use all of the observed data without excluding cases or filling in missing values to estimate the difference between the teaching programs in changing math skills. So Who's done a linear mixed model or any kind of mixed model here? See if don't know if people who are attending have. So yeah, it's often called maximum likelihood estimation to account for missing data, but a lot of the time you've probably done it and not actually realized you're accounting for missing data. There are still assumptions behind doing that, and that is that your data is missing at random or missing completely at random. And the missing data has to be only in your dependent variable. So yeah, this is, if you've done it, SPSS mixed models, LMER in R, proc mixed in SAS, or mixed in Stata, then you've done a linear mixed model. So this is like what the data might look like. Got the NAPLAN scores before and after, and in the control and the new program. And these blue dots are dots that don't have a partner. So they were only measured before or only measured after because they were absent. And then this is kind of what the results of a linear mixed model typically look like. And that's accounted for the missingness, assuming that the data is missing completely at random. So that's cool. Sometimes missing data is really, really easy to account for if you can make that assumption. Let's move on to aim 2. Is the program equally effective for students with differing levels of mathematical aptitude? So we have some different variables here. We have the same response variable, the same dependent variable, which is our NAPLAN score, which has some missing values, but we know that we can account for that using a mixed model. But now we have independent variables in addition to time, treatment group, student ID. We also have aptitude because we want to know whether the change in NAPLAN scores is different for students of both low and high aptitude. And there's missing values there. So we need a different approach. So this is where we come to imputing data. So who's heard of imputing data? Commonly known as making up data. But it's not just making it up. Imputing data is filling in the missing values according to some model. So here, we're going to assume that the aptitude scores are loosely correlated with the baseline scores. So we can fill in the missing values by estimating this relationship and then simulating from the model. So I've got a little graph that sort of shows you this. There's a loose correlation between the base scores and aptitude. So if we knew someone's base score, we could simulate a value of their aptitude. So if we knew the baseline score was 90, we could simulate a value for aptitude from a normal distribution with mean 103 and standard deviation 15. So sometimes it might come out to be 103, but it won't always be 103. It might be 110 or 85. And you'll get values centered on 103. So the software is going to do this for you when the time comes for doing this kind of analysis. You'll just need to think about the correct model for imputing aptitude, so imputing your missing values. So you'll need to tell the software that you think aptitude and software are linearly related, for example, and then it will simulate some values for you. So here I've imputed the missing values of aptitude for these different values, and I've used the base score as the thing to impute from. But if I just do it once, I've got a complete data set that I could do an analysis on. But if I if I impute the data again, I'll get a different result. So my results won't be very stable. So we want to have an analysis that's stable, like we can rerun it and get something that's quite similar. So the coefficient for the treatment effect won't change too much if we ran it again. And that's where we come to multiple imputation, which is where we'll run that simulation lots of times, like m times, and then we'll average across these. So if the number of imputations is large enough, we'll start to get fairly consistent results, which means that the coefficient representing the way the treatment effect depends on aptitude will be similar if we reran everything. So I'll just keep going, explaining multiple imputation. So we've simulated aptitude m times. So we now have m imputed data sets. And we're going to estimate the coefficient that we're interested in, m times. And then at the end, we're going to pull these m coefficients. So this is the diagram showing what we're doing. We start with incomplete data, one data set. It now becomes many data sets, the imputed data here, and we run our analysis to get many coefficients for our treatment effect, and then we go back to one treatment effect at the end.
A question online.
Yeah.
Dima asks how many imputations you should do, yeah?
I've got that coming in one slide. So yes, I will get to that very soon. So just to show you an example, these are the different coefficients that I got from running the education example different times. And each time I also got a standard error for my coefficient. And then we're going to go back to a pooled result. So I don't want you to worry too much about how we pool them. The most common way that you'll see done is with Rubin's rules from Rubin 1987, which there was a link to that earlier in the paper. Yeah, but basically you can take the average of your different estimates, and that's how you can get a pooled estimate of your treatment effect. But you also want to get variance of this pooled effect. So Rubin's rules estimates the variance of theta pooled. It's the within imputation variance plus the between imputation variance. And you need to estimate the degrees of freedom of this, and then it has a t-distribution, and then you can do confidence intervals, hypothesis tests, and everything that you want on your treatment effect. So there's I just want you to know that there are other specific settings when people do things different to Rubin's rules, but it's all along the lines of this idea of pooling both the mean and then calculating the variance of the pooled estimate. And you can assume that you will have software that is doing this for you. So you will have software that will run the analysis m times, pull it for you. The main thing that you need to focus on is coming up with the imputation model and also coming up with the model or the analysis that answers your research question. So those have to come from you, but actually doing the multiple imputation once you've got those two pieces in place, yeah, there's software that just does it for you. You don't need to worry about implementing that. And yeah, here I just want to round off that example to show we got this coefficient of 0.19. We got the variance of that pooled coefficient was 0.2. So we don't find any evidence that the new maths program depends on mathematical aptitude. It just works for everyone. So how many imputations? people do often do small numbers like 3 to 10 because in this classical paper, Rubin 1987, he said that this was enough. But more recent work does suggest that more imputations is a good amount. 3 to 10 doesn't seem like a lot to get a good estimate of the variance of the pooled estimate. There's no rule of thumb, even 20 to 100, that's a rule of thumb, and you might not need that many. The number of imputations that you actually need, it depends on the fraction of missing information. So that's the amount that the standard error of your treatment effect, the amount that that standard error would shrink if you had complete data compared to your data with all the missing values. So this fraction of missing information relates to how variable your coefficients are across imputations. And there's some really good links here on how many imputations to run that you can take out of these slides. They will go up online. But you can reduce the fraction of information missing if you have a better imputation model. So for example, with aptitude, we could come up with a better imputation model for aptitude if we included both the baseline scores and the end scores to try to impute aptitude. And that would probably reduce the between imputation variance a little bit. And you also reduce the fraction of missing information if you have less missing values. So yeah, the fraction of missing information isn't actually the fraction of missing data. It's the amount of information in that data that you're missing. Was there another question in the chat?
The question is what to do if the independent variables are categorical.
Yep. So categorical variables can also be imputed. You just need a different model. So I used a linear model to impute aptitude because it was a continuous variable. But categorical models can be imputed with, they often use machine learning kind of algorithms to like classification algorithms. So if you are trying to impute someone's discipline, say it's like an educational study and you want to, you don't know whether they're from science, maths or physics or chemistry, but you know what journals they've published in, so you could try to impute what faculty they're from so that you can use them in your study that needs that variable. Yeah, so there's just different models. So that's a hard question because it's actually, you're actually asking me a modeling question. Yeah, so there is, yeah, models to estimate categorical data. There's models to estimate binary data. So yeah, thinking about a good model for the missing variable with the missing data is, yeah, an important step. So let's recap what we've done. We've done a lot. Data can be missing completely at random. So when we can't use any of the other variables to predict whether the value is missing or not. If only the dependent variable has missing values and the missing values are missing completely at random, then you could try using maximum likelihood estimation, like a linear mixed model. You shouldn't, so listwise deletion is also an option because it won't cause bias, which is typically considered the bigger sin, but it can reduce your power. If your independent variables have missing values, then you can, or in other settings where a mixed model doesn't work, you can use multiple imputation. And if the data is missing completely at random, we can impute the missing values of one variable using the observed values of other variables that relate to that variable. So where are we going next? Data can be missing at random. This can cause biased coefficient estimates as well as increasing variance. If only the dependent variable has missing values and the missing values are missing at random, you can use maximum likelihood like a linear mixed model, just like when the data is missing completely at random. If the independent variables have missing values, then multiple imputation can be used. So you can impute the missing values of one variable using the values of the variables that relate to that variable. So where we're going next is missing at random is going to be really easy to handle now that we've done missing completely at random, because the main difference is whether you think that listwise deletion is okay. So if the data is missing at random, the propensity for a value to be missing or not is related to some of the observed data, but not the value itself. Just checking if there was another question that popped up. I already answered it. Cool. For example, the response rate for sensitive survey questions. There might be a question on a survey that women are less likely to answer than men. So the propensity for missing this depends on gender. And because we might know the gender of the people that complete the survey, we can predict how likely they are not to answer a particular question based on that other characteristic. Another example is where a mouse being used in a study on tumor growth was euthanized early because it reached a pre-specified humane endpoint. So the tumor went beyond a specific volume, and so they had to euthanize that mouse. So it wasn't the mouse dropping out of the study or anything, but we never got to measure the mouse on days 19 to 20, but we can predict that those values will be missing because we know the tumor volume on day 15. So that's also missing at random. Feel like something's gone wrong on my slide there, but I'm pretty sure the first dot point is saying something like it can lead to both biased and more variable parameter estimates. Now, I'm going to say that for tiny amounts of missing data, when it's missing at random, we might be willing to admit some bias anyway and use listwise deletion. But that's like tiny amounts. But for non-tiny amounts of missing data, you should use maximum likelihood estimation if possible, or multiple imputation. And tiny is definitely like less than 5%. That was for missing completely at random. When you're missing at random, I think you want to be a lot more conservative. And the reason that you might be willing to admit some bias is because sometimes doing multiple imputation does introduce variance, and that's annoying. So let's go back to our educational study. Now our study is taking place amongst high schoolers where truancy is not uncommon. So for example's sake, let's say these students, they don't know which days the assessments are taking place, so they're not purposefully trying to avoid the assessment, but they just don't come. And we start to worry that some of the students are not absent because they're sick. They might be skipping maths classes because they hate maths. So here's our example. The data's missing when the student are absent on assessment days. We can't just justify this, they're absent due to illness. They might be absent because they don't like maths classes. So that it might be related but we think that if we know their baseline test score or their endpoint test score or their aptitude score, we can predict the probability that their scores in any other variable will be missing. So we're going to assume it's missing at random. If we're happy with these assumptions, then we can analyze the data in the exact same way as we did when we assumed the data was missing completely at random. That is a linear mixed model for aim1 and multiple imputation for aim2, and get the same results. So just to recap, data can be missing completely at random or missing at random. When the data is missing at random, you can use listwise deletion, maximum likelihood estimation, or multiple imputation. When it's missing at random, you shouldn't use listwise deletion because you'll get bias. But otherwise, the approaches to analyzing the data are basically the same. So there's not too much grief over getting the missing mechanism wrong if you're not using listwise deletion. So data can also be missing not at random. And this is bad. bad, generally. This just generally gives us an icky feeling because we don't really have a way to know what was going on with the missing data. So, didn't do incremental dot points here. So missing not at random means that the propensity for the data to be missing depends on the value that's missing itself. So an example is a patient gets better from a treatment, so they stop coming in for their appointments in a longitudinal study, and we never find out their outcome. So the patients that didn't come in might have had the same trajectory and then got better as the ones that kept coming in. So who didn't get better? Another example is a student knows they're going to do badly on the test, so they skip the test, and we never find out how much their scores did not improve. And the reason why missing not at random data is so annoying is because we can't use our observed data that we have to impute the missing values. So we have to make up an imputation model, but it has to come a little bit from theory rather than data. And that feels a little bit uncomfortable. So, for example, with this educational example, students might be absent due to illness. They might be absent because they know that there's a test on and they know they haven't studied for it. And so the students who are absent are expected to have even lower scores than we might expect than knowing their previous scores and aptitude. And so this is missing not at random data. So how should we impute the students' scores who are missing now? So before, and sorry, this is the x-axis label is truncated. Before we imputed from the baseline scores, we might have imputed the end scores from the baseline scores. Now we kind of have to make something up. So we could come up with a model, for example, where the test score of the non-attenders is on average 60% of the test score of attenders, conditional on all other variables. And you can see I've put these blue dots in here. So say we knew that their baseline scores were along there, we're kind of imputing what their end score could have been, and it's going to come out a little bit below what we'd expect it to be with our imputation model. So yeah, but how do we know our model is right when we can't check it? So here's another example. This is a published study. It's called Missing Data in a Long Food Frequency Questionnaire. So people did this survey where they estimate the frequency that they consume different foods. And there was a lot of missing data. And what people typically do with this kind of data is that they assume that if you don't answer a question, you left it blank because you don't eat that food. So therefore, a value of 0 is imputed. So if the value for bananas was missing, they made it 0. So if you took this imputation approach, what kind of missing data are you assuming? I'm going to dare someone to leave it in the chat. No one? Yay, it's missing not at random. Yeah, because you're assuming it depends on that value and it's 0. So they're like, I don't even know what that food is, so I'm going to leave it blank. And that's because they don't eat it. So this study was really cool because they decided to check their assumptions. And what they actually did was they rang a random sample of respondents with any missing data, and they talked to most of these people. And then they found out what those values really should have been. And mostly the true values of the initially missing data for frequently eaten foods were mostly non-zero. But for infrequently eaten foods, they were often zeros. So you can see here the proportion of zeros. In the sample missing data, they initially estimated that 16% of people didn't eat bananas. But in the complete data, the estimated complete data, that dropped down to 5.8%. So this did lead to regression coefficients being quite different for commonly eaten foods, but not for rarely eaten foods. So yeah, the banana regression coefficient was initially underestimated by 22%. But it didn't change the coffee regression coefficient because mostly this was a specific cohort which doesn't consume coffee. They mostly had zeros for coffee anyway. So these study authors recommend guided multiple imputation, which is where you follow up a fraction of your missing data and then come up with a model for how to impute the rest of the missing data. Now, that's obviously a wonderful thing to do if you can. What happens when you can't check your assumptions? So I'm going to go through the one last example before I close this seminar. And this is also a real example. It's missing data in a medical context, and this is an unpublished study that I'm collaborating with someone on. And in this study, the patients have been divided into 2 groups, treatment and control. They underwent a medical procedure, and then they were invited back for a follow-up appointment to check on a metric of their severity of their symptoms. So yeah, because this study is not published, we're going to talk in general terms about it, but we'll call this score Y. That means how severe their symptoms are. Now, a large number of patients don't come back to the follow-up. So it was often 20%, but up to 50% of people didn't come back during the pandemic. And those patients during the pandemic were all in the treatment group. Now, across all time points, a large number of patients who do follow up are asymptomatic. So they have Y equal to 0. So, and this is what the missing data looks like. This is across time, and this is how much of the data was missing. So 20%, and then during 2020 and 2022, they had huge amounts of people who didn't come in. So the clinicians who are working on this study think that people without symptoms are less likely to follow up. Now, 60% of people without, a lot of people without symptoms are coming to the follow-up appointments, but they think that the people who aren't coming to the follow-up appointments, they probably don't have symptoms. If they had symptoms, they would come. So we think that the data is missing not at random, because it depends on their value of Y, whether they have symptoms or not. So one option for imputing Y is that we just set everyone to 0 for those that don't follow up. And the other option is that we sort of say it has the same kind of shape distribution of Y, where lots of people have 0 and some people have non-zeros, but the mean is going to be much lower in the missing population than the observed population. So we sort of like multiply the mean by some value that's less than 1 and then simulate some missing data from that. So we're planning to do this and present our results demonstrating the sensitivity to the assumptions. So this is just kind of like a template that we're working on for how we might present the results. We'll show different assumptions that we've made about the people who don't come back for their appointment. Those different assumptions will lead to slightly different methods. And then we'll report the treatment effects depending on what missing data imputation model we used. So the first one might just be setting everyone who didn't come back to have a value of 0. But then we'll say, well, what if some of them had symptoms and they just didn't come back because they didn't want to get COVID, or they, you know, they had something else on, like their family members were in isolation. So some of them may have had symptoms and wanted to come in for their appointment but didn't. Maybe there are people who just live with their symptoms and don't seek medical attention as well. So we'll test our assumption, we'll test the sensitivity of our analysis to those different assumptions. And this is sort of like doing another thing that you can do for missing data is a best and worst case sensitivity analysis. So this might mean that you run the model where everyone in your treatment group is sort of cured or has a good outcome, while everyone in your missing control group gets poor outcomes. And so that's like your best case for your treatment effect, and then you can reverse that and run it for your worst case, and then try to say something about where you think it's going to be. So that's the end. This is a huge topic, and this was by no means a comprehensive primer to missing data. So I'm sure I've missed things. And I'm sorry, I did say in the abstract I would touch on model selection, but it's just there was just too much to say. For specific guidance on missing data, you should come and talk to us at Stat Central, and we're always happy to do that. And yeah, I'm happy to take questions, and I hope that this seminar has been helpful to get you introduced to the concepts around missing data. Yeah. Thank you. I'll see if there's any chats. You're welcome. I can see lots of thank yous coming in. If you'd like to speak to us at Stat Central, we have our website with a book consultation button, and that'll take you to like a little web form, and you can put your details in there, and then that's kind of puts you into our system, and we'll get back in touch with you. And there's the link in the chat twice. Yeah. So We support all HDR students at UNSW. We support staff. So we have we have a lot of partner schools at UNSW. So if you're part of one of our partner schools, you are likely eligible for more assistance. And if you're not, you are also all eligible for study design advice as well. So we just can't, and we also do develop contracts with people where if it's more than just advice and more hours are needed to work on something, then we can often come up with an arrangement where you can contract us. But if you're a student, in any case, if you're not sure, put something into our request sheet because we can check your eligibility for support levels as well. Yeah. Cool.